One of the best-known examples of an event horizon derives from general relativity's description of a black hole, a celestial object so dense that no nearby matter or radiation can escape its gravitational field. Often, this is described as the boundary within which the black hole's escape velocity is greater than the speed of light. However, a more detailed description is that within this horizon, all light-like paths that light could take, and hence all paths in the forward light cones of particles within the horizon, are warped so as to fall farther into the hole. Once a particle is inside the horizon, moving into the hole is as inevitable as moving forward in time, no matter in what direction the particle is traveling, and can be thought of as equivalent to doing so. Depending on the spacetime coordinate system used, the surface at the Schwarzschild radius acts as an event horizon in a non-rotating body that fits inside this radius. Although a rotating black hole operates slightly differently, the Schwarzschild radius of an object is proportional to its mass. Theoretically, any amount of matter will become a black hole if compressed into a space that fits within its corresponding Schwarzschild radius. For the mass of the Sun, this radius is approximately 3 kilometers. 9 miles. For Earth, it is about 9 millimeters. 35 inches. In practice, however, neither Earth nor the Sun have the necessary mass, and, therefore, the necessary gravitational force, to overcome electron and neutron degeneracy pressure. The minimal mass required for a star to collapse beyond these pressures is the Tolman-Oppenheimer-Volkoff limit, which is approximately 3 solar masses. Quote, according to the fundamental gravitational collapse models, an event horizon forms before the singularity of a black hole. If all the stars in the Milky Way would gradually aggregate towards the galactic center while keeping their proportionate distances from each other, they will all fall within their joint Schwarzschild radius long before they are forced to collide. Up to the collapse in the far future, observers in a galaxy surrounded by an event horizon would proceed with their lives normally. Black hole event horizons are widely misunderstood. Common, although erroneous, is the notion that black holes vacuum up material in their neighborhood, where in fact they are no more capable of seeking out material to consume than any other gravitational attractor. As with any mass in the universe, matter must come within its gravitational scope for the possibility to exist of capture or consolidation with any other mass. Equally common is the idea that matter can be observed falling into a black hole. This is not possible. Astronomers can detect only accretion disks around black holes, where material moves with such speed that friction creates high-energy radiation that can be detected. Similarly, some matter from these accretion disks is forced out along the axis of spin of the black hole, creating visible jets when these streams interact with matter such as interstellar gas or when they happen to be aimed directly at Earth. Furthermore, a distant observer will never actually see something reach the horizon. Instead, while approaching the hole, the object will seem to go ever more slowly, while any light it emits will be further and further redshifted. Topologically, the event horizon is defined from the causal structure as the past null cone of future conformal time like infinity. The black hole event horizon is teleological in nature, meaning that we need to know the entire future spacetime of the universe to determine the current location of the horizon, which is essentially impossible. Because of the purely theoretical nature of the event horizon boundary, the traveling object does not necessarily experience strange effects and does, in fact, pass through the calculatory boundary in a finite amount of proper time.